Yeah.
There you go. Hello, everybody. It's a great pleasure to be here at this great conference on Phobos and Deimos. I'm going to show you some of the recent results we've had on a project that we started now a couple of years ago on trying to form Phobos and Deimos from a big disk around Mars. It's going to be a little bit of repetition on the background from what Pascal showed you, obviously, but hopefully not too much. So just a couple of properties for these moons. The most striking, I guess, is that their mass is very, very small compared to that of Mars, totaling only about 10 to the minus 8 times the mass of Mars. They have low densities. And a very striking feature that we've seen is that Phobos is inside co-rotation, but Deimos is outside co-rotation. And as Pascal showed earlier, even though Phobos is today pretty close to Mars, if we integrate back its orbit over 4 billion years, due to 4 billion years of tidal evolution, we think that when it formed, it was actually much closer to co-rotation, but still just inside of it. So, as we said, the origin of these bodies remain uncertain. Obviously, there's going to be a lot of discussion about this at this meeting, I expect. Generally, the in-type capture has been seen as suffering from a difficulty to explain the nearly circular orbits of the two satellites. But instead, if we can form maybe Phobos and Deimos in situ from a disk, we could have orbits that are already in the equatorial plane and possibly circular. So Craddock, as shown by Pascal, was one of the first to suggest that an impact with Mars could form a disk, but we point out that impacts that produce very low mass disk would generally not place material into orbit as distant as Deimos. And as Pascal showed, a low-mass compact disk could spawn moons, but they would be lost eventually to inward tidal involution and could not place satellites all the way into the current orbit of Deimos. And so back in 2014, we started investigating the formation of Phobos and Deimos for a massive extended disk whose outer edge would be already extending all the way to the current orbit of Deimos at 7 Mars radii. So we point out a couple of requirements for an impact origin. We want to have a large impact. Mars 25-hour day implies an impact with an object that's roughly a few percent of Mars's mass. And also the Broadleaf basin has been generally argued to be a signature of a large impact on Mars. The resulting disk mass would be much larger than that of Phobos and Deimos. Again, that should not be a problem because most of the material that would be inside the orbit of Phobos could have been lost by inward tidal decay. And finally, we want an outer edge of the disk that is located close to the orbit of Deimos. So we need initially material well outside the Roche limit, but we also do not want a disk that would extend much farther than the current orbit of Deimos, as satellites could have accreted beyond that orbit, and we don't see them today. And so finally, the idea is that Phobos and Deimos are simply the two last remainder of a once larger population of satellites. Just to point out a key difference in our modeling of the disk compared to the Rosenblatt and Charnot's paper that Pascal just showed. In our case, we do consider that the drop of mass from the disk from the inner region to the outer regions follows a most steady decline. And we do consider disk masses that are a little more massive than what the other model has been investigated. So we performed quite a number of SPH simulation of potential Phobos and Deimos forming impacts. We performed roughly 500,000 particle SPH simulations. We consider two types of impact, one that we call large, with an impact at 3% of Mars's mass, with a relatively low velocity. These are impacts that will be capable of producing Mars's day and also potentially the Broadleaf basin if we follow the Marinova et al. 2008 requirements to form that basin. But also we considered smaller high-velocity impactors, with the impactor mass being about 0.3% that of Mars. And these are the type of impacts that would be capable of producing Broadleaf basin if we follow the Nemo et al. 2008 estimates. So I'm going to show you a typical simulation from SPH. In that particular one, we use an impactor that's large, with 3% of Mars's mass. at a 45-degree angle and an impact velocity of the order of the escape velocity of the system. And you're already, I think, pretty familiar with all this animation that Rob and Canop has been doing extensively for the formation of the moon. In this particular run, the final planet has a day of about 24 hours, which is pretty close to the current one. We form a disk mass with roughly 10 to the minus 3 Mars masses, and we end up with about 350 particles in the disk, so that the disk structure is marginally resolved. I'm going to show you now a couple of graphs showing the trend in impact results based on the different impact configuration. On the left, you can see the disk mass in unit of planet mass as a function of the scaled impact parameters. The different colors show different impact velocities. The points are data for the large impactors comprising 0.3% of Mars's mass, and the triangle below are the small impactor containing 0.3% of Mars's mass. You can see that we form disk masses that range roughly from 10 to the minus 5 to 10 to the minus 3 Mars masses. And on the right, we show the disk radius in unit of Mars radii as a function of the disk mass normalized by the planet mass. And we can see that we form many disks whose outer edge is doing anything. It's not trying anything. Is there a laser pointer somewhere? Oh, there you go. Okay. Many disk edges that lie toward the orbit of Deimos at 7 Mars radii. So next up, we follow the accretion of Phobos and Deimos from the disk. To do that, we make use of a disk model that we originally developed to study the formation of Earth's moon from the prolunar disk. This is a hybrid type of modeling in which the material inside the Roche limit is modeled by a uniform disk that spreads viscously. This disk is contained inside the Roche limit here that we place at about 2.7 Mars radii. And beyond that orbit, we find many small individual particles whose orbit is tracked accurately with the n-body code SIMBA. The outer moonlets can interact with the inner disk via Lindblad resonances, and we also include the effect of tidal dissipation into Mars using the constant time lag model of Mignard, which results in the objects inside co-rotation here at 6 to have their orbit decay, while objects that are located beyond synchronous are going to have their orbit expanded due to tides. We want to point out that there's going to be an interesting battle between the disk torques and tides. We expect that satellites will grow from accumulation of the material in the outer disk, and the disk torque will tend to push these satellites away. However, once a body reaches a distance of about 4.2 Mars radii, all of its first-order Lindblad resonances will be outside of the disk, so it will not be interacting directly with the disk and will not be able to have its orbit expand further than this distance by direct interaction with the disk. However, additional expansion will be possible if that outer body captures an inner body into a mean-motion resonance, and if that inner body is itself interacting with the disk, then the outer body can also have its orbit being increased. And finally, the tides will pull the inner satellites inward. So what will be the balance between the disk torques and the tides? The current Mars tidal Q is expected to be within 10 to 100. What our concern is that if inner moons migrate away, they may end up accreting or scattering Phobos and Deimos type satellites. So this is the representation that I will be using in the next few slides. Here we show mass on the y-axis and Semimajor Axis in units of Mars radii on the x-axis. The orange slab here represents the disk inside the Roche limit, and all the different points are individual particles. The black line here represents the accumulated mass in bins of 0.1, this should be RSUB, and in bins of 0.1 Mars radii, which basically show you the decrease of mass as a function of distance. So first up, we look at accretion from a massive disk. We look at a disk that has roughly 10 to the minus 4 Mars masses with a mass ratio of 90% to 10 inside the Roche limit to 10% outside. And we use a tidal Q that's reasonably strong, around 15. And And we see that very, very massive satellites rapidly form inside, from the material outside the Roche limit, and they grow to be so big that they end up accreting all the material that is initially located beyond synchronous orbit, and do not allow any material to form Deimos-type satellites. Eventually, these satellites see their orbits decaying due to tidal interaction with Mars, and eventually we are left with a situation where we only have a massive disk inside the Roche limit that can spread viscously and spawn moons whose orbit cannot expand very far, which is what the Rosenblatt and Charles paper was showing. So next up, we look at a disk that's less massive. This is a disk that's an order of magnitude less massive than the previous one, totaling 10 to the minus 5 Mars masses, with the same mass ratio inside and outside the Roche limit. And in this particular run, we explore a tidal Q that is on the lower side of expected values for Mars. We can see in this simulation, we initially formed two bodies that are pretty good candidates to Phobos and Deimos. However, because of extensive expansion of the orbits of inner moons, we end up destroying that Phobos equivalent, and eventually, over millions of year timescale, due to inner moons being captured in mean motion resonance with outer moons and pushing them away, we end up losing material of these Deimos equivalent satellite over millions of years timescales as well. This can be seen particularly a little better on this graph. On the top graph, you can see the Semimajor Axis of various bodies as a function of time. The different black curves shows different bodies in the simulation. Here we have a merger between an inner moon and a slightly outer one, which merge to form what we call body number 3. And when that happens, that body number 3 ends up being captured in the 9-7 mean motion resonance with body number 2. And because that body is being pushed away, and because of the resonance configuration, it's pushing body number 2 farther away. And eventually, body number 2 is hitting the 3-2 mean motion resonance with Deimos, at which point Deimos' eccentricity gets highly excited, and Deimos ends up being accreted by the inner satellite. So finally, we look at a last case where we look at the same disk mass but crank up the tidal Q to the higher value that can be expected for Mars. Can the assistants start that movie? There you go. So we end up again forming two small satellites, but because tides are much stronger in this case, we do not have a significant orbital expansion of the inner moons that very rapidly tidally decay inside towards Mars and get destroyed. And eventually the disk spreads back to the Roche limit and also starts producing a second generation of moons from accumulation of material at the Roche limit. But because of the strong tides, these objects cannot move away very far, and we end up preserving two objects close to the expected initial position of Phobos and Deimos. So in summary, we find many impacts which are compatible with Mars's rotation that can also form extended disks. We will need higher resolution runs to better constrain the structure of the disk, particularly in the low disk mass cases. We do point out that in our study of this of the accretion of Phobos and Deimos for the disk, it seems that the survival of the objects requires strong tides and a disk mass that's toward the lower end of what impact simulation suggests. But we do also find many cases, particularly cases with weaker tides or more massive disks, in which the formation of Phobos and Deimos does not seem to be possible. And with that, I'll take questions. Thank you.
Morning. Just a question in terms of the impacts that you modeled. Can you describe a little bit more about the types of impacts? Could other types of impacts, say like a grazing impact, higher velocity, different parameters of the impact, change the results? And are you going to explore that further? Yeah, basically there's there's two parameters. There's the total angular momentum of the impact configuration and the energy. More grazing impact, I think, generally tend to form more extended disks.
and more head-on impacts tend to form more massive disks. So this is what I was showing with the impact parameters. So we've already been looking at how the disk mass varies as the function of the impact parameters. Yeah, so we're still exploring the space of parameters, but we're a little limited by resolution here. So I think specifically to look at runs that we're going to produce that involve less mass, we're going to need to increase the resolution to better see the structure of the disk.
Okay. Do you have the range of impact velocities that you assumed?
Like,
I might have missed that. Sorry.
Yeah. Can I move back? It's not moving back. Oh, there you go. Oops. Yeah, so we looked at impact velocities between 1 and 4 times the escape velocity.
Do you have those in absolute terms by any chance? I don't recall what the escape velocity is for Mars.
Yeah, around 5. So between 5 and 20 kilometers per second.
Okay, so higher velocity impacts, say from a cometary body, you haven't looked at yet.
You mean like 40, 50?
40, 60, 70?
No.
Yeah, okay.
Thank you.
Phobos, weak and creaky.
Weak and creaky. So let's see, what do I do here? That. So as much as I love giant impacts, I've